and welcome to our video on energy diagrams. In this video, we'll talk about the basics of energy diagrams and how to draw them, and I'll be using specific examples for SN1 and SN2 reactions. Even though we're going to use the specific examples, you should know that this process will work for basically any reaction once you learn the steps and what you're supposed to label and draw. So let's go ahead and get right into it. So before we get started drawing energy diagrams, we should probably review what they actually are. So an energy diagram is something that shows the progress of a reaction. It's going to show the different steps based on the energy levels that each part of the reaction would have. So really for us in organic chemistry, the most important thing we're going to be doing is relating the mechanism steps that we've talked about to the molecule stability, which is something else we've talked about. So we're really bringing together two things you should already know something about in a different way. So let's get started with an SN2 example just because they're a little bit simpler. So for the SN2 example, the first thing we really need to know is the mechanism. So you may not have to show it on the problem, but you would need to know what it is. So let's just go ahead and go through the mechanism. So for this mechanism, we should start off by identifying what type of nucleophile we have, since that will affect the mechanism. So is this a strong or a weak nucleophile? Right, it's a strong nucleophile. So that means that we want to redraw the nucleophile as a minus charge instead of with the sodium there. So we'll do that. And then what's going to be the first step of this mechanism? Right, the nucleophile is going to attack the carbon with the leaving group, and then the leaving group leaves. And then that's basically all you have, right? For this mechanism, there's only one step. So then the mechanism's done. So after we have the mechanism done, we're going to see if we have intermediates. Now in this case, we don't have anything, right? Because there's nothing in between the reactants and the product. There's no other steps. So basically we just have none. So I'm just going to write none here. Then the next thing we want to do is draw the transition states. So to draw a transition state, basically you're showing what happens between one step and the next step. So you're going to have partial bonds and partial charges, kind of like we did whenever we did resonance hybrids. Okay? So let's draw that. So the first transition state, we'll put it over here, is going to be these carbons stay the same, right? And then the bonds that are breaking are going to be a dotted line. So what bonds are breaking? Right, it's going to be the carbon Br bond. So we'll draw a dotted line for that. And then you want to draw a dotted line for any bonds that are forming. So which bonds are forming? Right, in the product we have a bond between the CN and that same carbon. So that'll also be a dotted line. So I'm going to draw that here. Then the last thing you want to do is check the charges. Now in this case, I didn't draw the byproduct, so I'm going to go ahead and draw that up here. And then that has a charge, just I need to know that. So if I'm drawing the partial charges, anything that had a charge in the step before in the product it makes is going to be a partial charge. So the Br minus would be a partial charge because it has a minus in the product. And then the Cn has a minus charge in the starting material, so that's going to be a partial charge also. And then that's all you have. So that's the transition state. So that's it for how much things you have to really draw. Now we need to draw the energy diagram line, but we're also going to label it. That's going to be really important. So the energy diagram is going to look like this. Always the axes are going to be the same. So the y-axis is going to be the change in energy. And then the x-axis is going to be reaction progress. Sometimes they'll say reaction coordinate, but I usually say reaction progress. Okay? So in this case, we're always going to assume that we're going to have an exothermic reaction because it goes forward pretty easily. And I know the SN2s are thermodynamically more stable, so that's going to be an exothermic reaction. So what does that mean? It basically means the reactant and the products are going to be different energies, and the reactant's going to be a higher energy than the product. So it's going to go downhill. Okay? So then if I had any intermediates, I would add those now, but I don't really have any. So basically in between the reactant and the product, the energy actually goes up first to make the transition state, and then it comes back down. So basically we're just going to have a hill that goes up and then comes back down. Now, the other things we need to label on here. So on the left side, you're going to have the reactants. So we'll label that. And on the right side at the very end is going to be the product, so we'll label that. Then at the very top of this peak is going to be the transition state that we drew. So I drew it over here. So we'll just write TS1. We'll just have a code. Makes it easier. Also, after I label the transition states, I would go ahead and label any intermediates. In this case, we don't have any, but just for future reference. Okay. The other thing you want to make sure you label is the activation energy. So the activation energy is the energy it takes to go from one step that you have to get over that hump to get to the next step. So basically it's going to be here, would be between here and here. The reason that the activation energy is important is because it affects the kinetics. It affects how quickly the reaction is going to go. So the biggest reaction activation energy is going to be the hindering part, the part that makes it hardest. And that's going to basically make it go from here to here at a different speed if we change that activation energy. Okay? So then that's all you have to label. So we've got the products, the reactants, the transition state, and the activation energy. Now, if we had any intermediates, we would label those also, but this example doesn't have them. So we'll see some more of those in the future. Okay, so hopefully that makes sense. Let's look at an example for an SN1 for comparison. All right, so now that we've sort of got the basics of the energy diagram and transition states, let's look at another example, but this time in SN1. So as we might recall, an SN1 mechanism is a little bit more complicated. So let's go through that first. So if we look at the nucleophile, generally for an SN1, you're usually going to have a weak nucleophile. The other thing that we'll always see for an SN1 is that you have steric hindrance around the leaving group. So like this is tertiary, for example. So it's got to be an SN1. The nucleophile can't fit in for backside attack, so that's how we know it's going to be SN1. So because the nucleophile cannot attack first, what is going to happen? Right, the leaving group leaves. So the leaving group leaves, and that's going to make a carbocation, right? So I'm going to draw all the same carbons, but just draw a positive charge here. All right? So then once I have that carbocation, now the nucleophile can attack. So the nucleophile, I'm going to draw the lone pair. It'll attack the carbocation, the carbon with the positive charge, and then that'll be the next step. And then what does that make? Right, it should look at a structure like this, where the oxygen is attached where the carbocation was, and then where should I have a charge? Right, on the positive on the oxygen, right? So, because that's where electrons went away from. So what's the very last thing I need to do to get to the product? What kind of step? Right, it's going to be an acid-base step. So the base is going to be the nucleophile, so just redraw whatever the nucleophile is, because that's the strongest base in solution right now. And then that's going to attack here to get the hydrogen and then break the bond. Okay, great. So I am going to go ahead and draw the byproduct now because we know we're going to need it for the transition state. So I'll just go ahead and draw that over here. It's not required for a mechanism question, but it is required for getting the transition state. So we're done with the mechanism, but before we draw the transition state, let's label the intermediates. So remember for the SN2 we showed before, there were no intermediates. There were no things in between the starting material and the product. But now there are, so we'll just label them so that way when we do the energy diagram that we can match them. So basically any structure you have in the mechanism that you drew is the intermediate. So I'll label this as intermediate 1 and this as intermediate 2, okay? And then the transition states will be in between like the starting material and intermediate 1, and then there'll be another transition state in between intermediate 1 and intermediate 2, etc. Okay, great. Okay, so now let's go ahead and draw the transition states. So the transition states, like I said, we're going in between two steps. So we're going to be going in between this part and this part for the first transition state, but there's going to be more than one, okay? So for this one, we're going to draw all the carbons that don't change. So we'll go ahead and draw those. I'll draw them in this format. You could draw them in the one at the bottom, but either way is fine, okay? And then what bonds are we breaking, right? The bromine, so we're going to have a dotted line for that and draw the bromine. We aren't making any bonds, so that's the only dotted line. Then what partial charges do we have? Right, we're going to have a partial negative charge on the bromine because that becomes a negative charge over in this part. I can draw that there. And then what's the charge I'm going to form in the next step? It's a positive, right, for the carbocation. So I also need to put a partial positive charge on this structure. That's transition state 1. We can label it. So then the next transition state is for the second step where the OH part of the alcohol is attacking the carbocation. So again, I'm going to draw all the carbons like that. And then I'm going to draw my alcohol, and then I'm going to draw my dotted line. So the only thing I'm doing in this step is forming a bond between the O and the carbon of the carbocation, right? So that's my dotted line, and then where will my partial charges be? Right, so I should have a partial charge where the carbocation was, right? That's a partial positive. And then I should also have a charge between the oxygen, because that's going to form a positive charge in the next step, right? Perfect, okay. So the last thing is the transition state for the acid-base reaction. So I'm going to draw my structure of all the bonds that don't change. So all my carbons with the O and the carbons on there. And then I'm actually going to be breaking a bond with that hydrogen, right? So I'll put a dotted line here with a hydrogen. And then I'm forming a bond with the O and the hydrogen, right? That's my byproduct thing I'm making. So I'm going to put a dotted line there also. okay? So then I have charges. What charges do I have? Right, I have a partial charge on this oxygen, and I also have a partial charge on this oxygen. So just remember, partial charges, look on both sides of the step to see where you're going to have the charges. For dotted lines, pretty much anywhere there's an arrow, there's going to be a dotted line, right? Because you're either breaking a bond or making a bond, and we use arrows to do that. So that's another way you can sort of make sure you have everything you need. All right, so that's all three of our transition states. 1, 2, 3. All right, so now let's draw our energy diagram based off of this. So just as a reminder, I put the steps up here that we used for the last one, so we'll just follow those. So the first thing we're going to do is label the axes, right? Then we'll label the reactants and products. So at the beginning is the reactants, at the end is going to be the products. I know I'm going to need more space, so I'll just leave it over here, right? So then how many transition states and intermediates do we need? Let's just count them. So for the intermediates, I should have 2, right? So I need to have 2 sort of wells. And then the transition states, I need 3 humps. So we'll just add the intermediates first, and then we'll do the transition states, okay? So if I have, this is my reactants, is my intermediate 1 going to be higher energy or lower energy than my reactants? So it's a carbocation, so that doesn't have an octet, so that should be less stable than the starting materials, right? So I'm going to put that higher than the reactants. All right, so let's look at the next one, intermediate 2. Compared to intermediate 1, do you think that's going to be higher in energy or lower in energy? So in this case, the O has a positive, which is more electronegative, but it also has an octet. So which is more important? It's the octet, right? So because oxygen plus has an octet, that's going to be more stable than a carbocation. So it should be lower in energy than intermediate 1. So it's important that we get the energies lined up correctly. That's going to be part of your points, okay? So now I just showed these dotted lines just to show the energy differences. I'm not going to put those on my final thing. I'm just showing it for right now. So you can tell like intermediate 1's higher than intermediate 2, but I'll erase them at the end. So now is intermediate 2 going to be higher or lower than the reactants? It should be higher than the reactants though, because it still has a positive charge, right? Whereas the starting materials have 0 formal charge. If your original reactant was a little bit high and you're like going to go off scale, you can always erase that and move it later. So one more reason to use a pencil. Just make sure it's not too high or too low. All right, so then my transition state should just go up in between and then down to the intermediate and then up to the next one. So I'm just going to add humps in here. For this one, I still need to draw my products, so I'll put that. Remember, it's exothermic, so it should be lower than the reactants, so we'll put it down here. And then I'll have one more transition state in between those where I'll connect those. The height of the humps, relatively speaking, isn't a huge deal to me. Technically, the first one will be higher because it's a higher intermediate, etc. But that's all you need to know. Okay? So then now all we have to do is add our labels. So I had already added the labels for the transition states in the intermediate, as well as the reactants, products, and the axes, all that stuff. And then the last thing is we'll put our activation energy on there, right? So we'll add those there, there, and there. So in this case, there's 3 of them, so we'll call them activation energy 1, 2, and 3. All right, great. So hopefully that makes sense. Like I said, it's a little bit more complicated for SN1, but if you know the basics, it's not too hard. All right, great. All right, so now hopefully you feel like you're getting the hang of these energy diagrams and the process of drawing the transition states and the energy levels for the different pieces of that. I just wanted to make sure that we think about, we might have some other examples that we might see in the future. So for example, we might see an SN2 with a weak nucleophile instead of a strong nucleophile. So we know the mechanism is going to be different, right? So we're going to have an SN2 step and then also an acid-base step. So that's going to change the amount of intermediates and transition states that we have. So what do we need to do when we're thinking about how we're going to set this up and how it's going to be different? All right, so obviously we're going to have to think about the mechanism and use that to determine how many intermediates we're going to have. So how many structures do we draw in the mechanism between the starting material and the product? Then after that, we'll consider how many transition states we have. So we're going to have the intermediates plus 1, basically, and we'll want to be able to draw all those. That's important. And then the last thing is you want to consider the energy levels of the intermediates before you add them to the energy diagram, right? So you want to basically think about the rules of stability that we learned way back in resonance and comparing those forms. So the most important thing is octet. The next thing is that you have the lowest formal charge. And then if there's a tie between formal charges, you'd look at the best formal charge. All right, so hopefully this was helpful. Let me know if you have any questions as usual, and have a great day. Bye.